So now we go on to the more formal aspects, and luckily this book of Ramon has a nice a bridge to going from single particle quantum mechanics to the field theory. So towards transition to the quantum theory, and let me also make some pre-remarks and then repeat them again, because these are very important remarks without which we will all get lost in formalism. So some remarks can be repeated. So we can say towards QFT Green's functions. So in QFT, we find that on this set, okay, the set with all possible values of n captures all the physical effects of the theory. So the purpose of quantum field theory, or any theory that you have, any quantum theory that you have, is to be able to calculate endpoint functions. What they mean and how we use them will come out later, but you can just think about the fact that if you had some very general function, if you know all its moments in sense of statistics, then you can always recover the original function. So the contents are all in all the endpoint functions, and that is what we are going to move towards. And towards that, let me also give away the other main trick. So the way we calculate this is to define a generating function. Now generating function will mean that we introduce an auxiliary variable actually auxiliary function, some f of t. Okay, we have q of t, p of t, but there is some forcing function f of t, and then we define in the presence of f, right, are all brackets here, yeah, to be equal to integral dp dq o e raised to I times s And now on we can say farewell to H cross, no more H cross, okay. Is and plus Is of PQ, and we add to this I times, so S you remember as integral dt of PQ dot minus H. So here we need to add an integral dt of f of t times the q of t, and whatever ti to tf. Yes. Also, actually, we are going to get rid of the momentum. So we can do two things. We can add some variable for plus I times. So we can add auxiliary functions f of t and g of t, which keep track of each of these. And this whole thing became too big, but you know what is going on, right? So it's all in the exponent. Okay. But to not get carried away with too much generality, we will in practice be using only the position dependent path integral. So, the more important thing, the denominator. Okay. So, but divided by dp dq of e raised to is of pq plus I integral fq plus I integral gp. So you have to divide out by the thing without the insertion of O. Now we shall be using the path integral only in the Q formalism. Where A, B are the degrees of freedom, then the path integral can be written only in terms of Q. Okay. This was exercise 1 last time, which I am sure all of you worked out the same evening. So, up to an overall normalization n, we write times O. and we would have the same n aside from some product, some multiplicative factors of measure 0 because of the slices where that enters. But as we said, so we define it like this, okay, we don't struggle over the fact that the front factor is going to look the same. So that's what it is. If this is how we define it, then, and so this was in presence of f, then what we can see is that this is actually equal to the same as, yeah, so the denominator yeah. And times, to get the O of Q down, all I have to do is differentiate this expression with respect to f enough number of times, okay, and I will backtrack a little bit. I will say that we will define this without the denominator, okay. So we, for simplicity, so this is technically how it is defined, I mean in real life to calculate averages, but for the time being we define also begin by considering just Q. Yes. So the main trick I am about to talk about is that the expectation value of Q of t then is simply equal to variation with respect to f of t of this object. So let us write q dot, s of q dot, and plus it remains and this is in presence of f. If you want to calculate and some factor I have to remove. So since there is an I over here, so it is actually variation which is I, can you put an there. This is clear, right? Because if you vary with respect to f, then a Q will come down and it will automatically reproduce this where O is Q, and then the exponential will remain as it is. So, and this is standard StatMech trick, right? So that's all we are using. So, and likewise, let's say Qt1, Qt2 would be equal to d squared of I delta f of T1, I delta f of T2 times the functional integral. Okay. So now what we will do is to introduce the harmonic oscillator in this language as a warm up to the real thing. We will find that there is a nice analogy of non-relativistic harmonic oscillator to the relativistic propagator, because the relativistic propagator is of the form p0 square minus p vector squared, that acts like omega squared plus p squared. The harmonic oscillator Hamiltonian is quadratic in Q and P, so it matches exactly. So now consider taking the harmonic oscillator relativistic field. I hope. And as you good students remember, there is D below them, but we have stopped writing it because it just becomes cumbersome. So this transition amplitude in this case is, aside from the n which we accumulate due to the momentum space integration, and we put that QTFT in. So for convenience we set m equal to 1, and we also introduce a m equal to 1. But most important thing is introduce a damping factor. E raised to minus epsilon, and we put it proportional to q squared. Or I shouldn't call it factor, but yeah, it becomes factor in the exponential. So then this is equal to 1/2 of q dot squared and then minus omega squared, but there is also minus epsilon q squared. So this minus sign I write as I times I, but that is with a plus sign. So omega squared minus I epsilon times q squared and then plus fq. So this whole thing dt. So note that this epsilon is such that as if you extend the Ti to Tf to very large values and it picks up a large contribution to this, then it will make the path integral go to 0. It will make it converge in the limit of Ti and Tf going to infinity. But we put it also not because we are worried about our mathematician friends and convergence or anything. It's actually a very clever device which comes useful. But it shows that to tell you, because you already know from quantum theory, in the Feynman propagator you have to have the I epsilon prescription, p square minus m square plus I epsilon. That I epsilon comes out exactly correct with the correct sign if you pretend to tell people, look, I am regulating this by putting a damping factor. So that is what is nice about the path integral. Okay. So now next thing we need to do is rewrite this in terms of energy integrals. So since we are coming closer to end of the class time, what I will do is I will write what we are going towards and we will prove the formulae next time. So what we can show using this is that limit of times going to infinity in the presence of f is equal to qf infinity qi minus infinity without anything times n e raised to, so f equal to 0 times e raised to minus I over 2 integral of dE f tilde e and f tilde of minus e. This you would be familiar with Fourier transform. You get opposite signs when there is product of things, divided by e square minus omega square plus I epsilon, where the f tilde are just Fourier transform. Use minus IET. So the point is that this object that was to be computed, if you just did the without any f, then the answer for O cannot depend on any q of t, right? Because q of t got integrated out. There is a big integral over dq of t. So the meaning of what we are calculating becomes clear if you insert this f as a temporary device and then drop the f in the end after you have calculated. So here I should have said one more step was here. These are still in the presence of f, but to get it in the end without any f, what you have to do is this and then evaluate it at f equal to 0. That is the prescription. So the f is so right now we can see that this expression in the presence of f has no q of t in it, okay, and it's a function of, in fact, just the f, it's Fourier transform, but it's function only of f. There is no sign of any q in it, but we can now compute the expectation value of qt1, qt2, etc. by just varying with respect to ft1, ft2. Of course, they are Fourier transforms of this variable, but you can extract the 2-point functions out of this. So thus we have a of f of t Right. So this is the meaning of, this is what we call generating functional or generating function, from which by varying the auxiliary variable we can extract the endpoint averages. So it contains all the information that you need to calculate all the physical quantities of interest. Okay, so from here on I am actually just using Ramon's book for next couple of turns, so you can read it, and the comments that I have been making about momentum space, the canonical path integral, the phase space path integral as being the correct thing is also commented by him. He derives it using more like the more intuitive Feynman approach and assuming that it is given by Lagrangian. But then before switching on to these topics, there is a short discussion of why actually you have to use the P. If you don't, then you get some spurious factors, which usually don't bother you ever, but for keeping things straight, and then you don't have to put any n at all, you get the exact answer.